All right, let's have an example of multiple imputation. The data set we're going to look at includes a number of variables. We're going to look at variables related to depression and abuse history. And we're going to ask whether depression differs based on history of abuse. Just some initial diagnostics here. These are the variables that had missing data. So we can see, there's no more than 67 missing cases on any one variable. But overall in this data set, there's only 296 total complete cases. So there's a lot more missing data. So the individual ones, this kind of builds up, and we get like 30 or 40% of our data lost. I'll talk about two packages for multiple imputation. The first one is called Amelia, named after Amelia Earhart, who went missing. Get it? And Zelig, named after a movie. I'll comment more on that later. Amelia does the imputations and the diagnostics. Zelig does the pooling. There's additional commands to identify non-numeric variables or factors, diagnostics. And it's kind of funny. I often hear that these approaches are too complicated for most researchers, but just look at this code. MI, the Amelia command, name of the data set, M, that's the number of imputations. Noms, what are the nominal variables? If you have a variable that captures ID number, you tell it what it is. Boom, that's it. That's it for doing the multiple imputation. Then to run the analyses, to pool the analyses, it's just the Zelig command. Your analysis, model ls, least squares. What's the name of the data? The data is called MI, and then we summarize it. So again, what we see here is that this isn't that complicated. It's actually pretty easy to set this stuff up. When you run the Amelia command, you'll get something that looks like this. It just goes on and on and on and on and on until it does its 20 imputations, so you can watch it as it goes. I found that Amelia can be a little slow, although I like it. I like it better than another package called Mice. Amelia can be a little slow. Mice is certainly the faster of the two packages. If you have a preference. And we'll probably take a look at some Mice code later in the semester as well. So before jumping in and doing our analysis, and pooling the data for our final answer, we want to go to the diagnostic phase. This is where we ask explicitly, okay, did this work? And how are we going to get at that question? Well, there's two things we can look at. First, are the estimates we get stable? Does it quickly come to a solution, and does it stay solved? And then we can compare the imputed and the actual values. So we want those imputed values to have basically the same distribution or be within the same boundaries as the actual values in our data set. If they're not, we know that those can't be good estimates. So if we get a look at those two things, we're going to be in pretty good shape. So first one, on the left, this is called over-dispersed start values. Don't worry too much about this. What we're looking for is we'll have that fan shape on the left, and they all come together and they land. And the question isn't whether they land or not, but whether they stay in the same place or whether they start to pop up again. The one on the left, this is our data. What it shows is something that is converged. This is what you normally get, unless you have really weird data. The one on the right is an example of a problematic one. You can see that this converged, and then we've got two variables that jumped away. So that's, again, a problem there. We want to see it remain stable. So that's really all we're looking for here. And then the actual versus the imputed values. We're looking to see that the black, which are the imputed values, roughly matches the actual distribution. So we can see here, yeah, the black is mostly covered by the actual distribution in red. Don't worry about this being kind of lumpy. The reason why it's lumpy is that there's fewer estimates. So we can see it looks fine for this variable. This variable looks like it's relatively well covered. And then finally, the last one looks like it's good. What we don't want to see is something that might look like this. You can see the actual values are way out. I'm sorry, the imputed values in the black are are often way outside of what the actual values are. So that's what a problem would look like here. And someone always asks in class, well, what do we do if we have this problem? And I have no idea. I think that your data are so messed up in this case that you might have to throw it away. All right, running the analyses. This piece here, this is a loop. What I'm doing is I'm having R build a variable called BDS that's inside of my imputed data set. And what that's going to be is just a sum of all of those individual depression items, much like you would do when you've got your own scale. But here I have to do it in a loop because the way the data file looks for an imputed data set, it's got imputation 1, imputation 2, imputation 3 as you know, kind of sub files. So I've got to feed it something that looks like this. This took me way too long to figure out, but it's really helpful now that I have it. So we're taking those imputed ones, those complete cases, and we're building that composite measure from it. We'll see with ML, we can do this a little differently. Next, we do the Zelig command. And you'll see you've got BDS, predicted by abuse. Model is LS for least squares. You can do all kinds of different analyses here. Tell it the data. This is the imputed data we do it with. Then we summarize it. We see we get a Z value here. These are the pooled results. Combined imputations. So we have a significant result, Z of about 7.2. Just to give you the original data for comparison, these would be the data without any sort of imputation. You can see we get actually a smaller t-value. And that smaller t-value is really a product of the difference in the size of samples. The sample size is returned to full for this analysis, which means smaller standard errors. And the Z and the t values, they're different scales, but you can basically compare them directly in this case.